is that all the pi bonds have these p orbitals that can overlap to a sufficient degree to have bonding molecular orbitals, meaning no interference, right? Yeah, these are possible configurations, but they don't need to go into those configurations because they can distribute all of those pi electrons in these lower energy levels.
So if there's nothing holding them in a higher energy level, will they naturally like fall back down?
Yeah,
to the
this
lower one?
is their, and as you know, molecules don't want to exert any more energy than they have to, right? So if you have something that has a lot of constrained parameters to it, it's not going to be stable, right? Cyclobutene, just a box, right?
Yeah.
And 90-degree angles
Right.
aren't. I use a lot of. I'm kind of anthropomorphic. I don't know if Sean is or not. It's probably not great, but like I like to think of these things as being happy or not happy, right? They aren't happy, even though they actually don't have emotions, right? But this doesn't exist in nature very readily.
It's not worth it.
No, it's not worth it. It will break apart into other things, like maybe ethane. Okay. And so you had mentioned, Rob, that you had some questions about the nodes and stuff. So I mentioned that I would kind of find some slides and do a quick review on that. So this is just a couple slides here.
Cool. Thanks.
Going into this. I didn't put it on in the slide deck. This is a previous slide deck. But essentially, these pi orbitals are going to overlap. And if they're all in the same orientation, then you get complete overlap, right? And that's great. So this is showing that all the red portion of that p orbital is up, and the blue is down, so everything is essentially in phase. Okay? And so there's no interference that is caused when we then take these pi orbitals and start flipping them. Okay? So this happy. This less happy, right? And as a result, we say that there's an interference, or in other words, a node is caused.
So each node is like a interface of interference.
Yeah. So if it's like this, and we have no interference, complete overlap, right? So this is kind of like what's showing here.
Yeah.
But if this were to flip, then now we have interference here.
Okay.
And I think Sean probably went into things like you had mentioned, closing the ring. Right? When you close the ring, depends on if it's con rotary,
right,
or syn rotary. One going a different direction, and then that's going to create certain issues.
Okay. Yeah, electrocyclic.
Yeah. Now, this is the last slide I want to show. Right. So, depending on how many p orbitals you have, you can have different numbers of nodes depending on how these things are flipped or not. Right? If none of them are flipped, then you have total overlap. And that's going to be all bonding molecular orbitals, and it's going to be stable, no interference. Right? If you have something where it's just flipped here, then that just creates one node of interference, and that's going to be less stable than no nodes, but more stable than multiple nodes. So the more nodes we get, the more we get into that anti-bonding realm, the less stable that molecule is going to be.
Sure.
And so here each one of them are alternating, and so there's going to be 3 notes.
So when they're alternating, do they kind of like repel each other a little bit, or are they just not forming a molecular orbit?
Yeah, so it really has to do, it's kind of an arbitrary thing. But we call it up and down spin, right?
Okay, yeah.
So it depends, it's their direction of movement, right?
Okay.
And there will be this repulsion, and it's kind of analogous to a musical string, okay? So guitar string or violin string or anything like that, the way it makes sound is a vibration, right? You pluck it, or you take your bow, and you can change the frequency by sliding your finger up and down that neck, right? Well, there are these. You guys play instruments at all?
I used to play
Okay,
guitar.
so you
I'm not
kinda know what I'm
very
talking
good.
about.
Yeah.
There's this aspect called harmonics. So I don't want to get too off track.
Yeah.
But a stringed instrument has frets usually. Some are fretless, but in other words, when you're holding down that string, you want to put it somewhere in between these frets. Okay? And as you shorten the string, the pitch gets higher because the frequency gets higher, right? But if you were to go up to a certain distance on that neck and just put your finger on the string lightly and pluck it, you get what's called a harmonic sound.
Yeah. The high pitch. Yeah.
The high pitch, and that's because you're actually creating interference
Okay.
at that distance. Okay, because you can't really do harmonics anywhere. You've got to do harmonics at a certain part along that neck. Okay, because of the way the frequency, which is a wavelength,
Right.
the way it creates interference with itself
Okay.
will give that other pitch.
So it like has to overlap at a certain.
At a
The
certain
frequencies have to
space,
overlap correctly.
right?
Yeah.
And so same kind of thing here.
Okay.
There's a vibrational interference because of the movement of the electrons, and yes, there's disagreement, they're repelling.
Okay.
And so that's what's creating those.
Okay. Yeah. Thanks for getting into detail. Yeah. It's just like a weird thing to conceptualize. Yeah.
Absolutely. Like I said, molecular orbital theory is complex.
Yeah.
We're just kind of mentioning it a bit, but not getting into the specifics.
Yeah.
All right. So this is benzene, but what about cyclobutadiene? Well, cyclobutadiene is actually a lot like cyclobutane, butane only, right? It's got diene, so it's got 2 pi bonds on opposite sides. This is going to have a distribution of the pi bond electrons that looks like this. And this is called a Frost circle. Okay. So you can actually draw these out. Hey, Nikki, we just kind of went over nodes a little bit, so you didn't really miss much, okay?
Sorry, I had a dentist appointment.
All right.
I just didn't think it was gonna take that long.
Cavities.
No cavities.
All right,
Good
good.
news.
So if you were looking at this, these energy levels, you could draw I should probably not get in the habit of drawing on this. I guess look up how you get in trouble. You can draw out. I wonder if there's a way to draw on this though.
Will it project on the whiteboard from the big projector?
Well, I don't know if it will. We could try it. I just don't know if I can do that and keep the screen.
Oh, right.
I definitely don't want to draw on that screen.
Yeah.
Let's see. Okay. All displays on. But now,
That comes down automatically.
go up.
Oh,
Okay, cool. Good thinking, Rob.
Turn off.
All right. All right, so that's not too bad. Just cutting off the title a little bit, but you get the whole thing there. Yeah, so if you were to connect all these orbitals, what do we get? Shape of benzene, right? Okay. Now, if we were to go to cyclobutadiene, it's a different Frost circle, right? We've got those orbitals arranged differently. But you can still draw that structure. Right? There's our cyclobutadiene without the double bonds in there. Okay? But look what's happening. Because of this, the way that the pi bonds or the pi electrons are distributed, we do have one in the bonding molecular orbital, but the other two then are in non-bonding, which isn't great. Okay? And if you guys remember from Gen Chem, you got to fill these things up first before you then put another electron in that orbital.
So
right?
is there the same energy level, the 2 and 3?
Mhm.
Okay.
And so these are no longer paired up. So in addition to having that constrained bond angle of 90 degrees, you also have non-bonding pi electrons. And so as a result, now it's not going to be nearly as stable as cyclooctatetraene. So octa, right? It's an octagon. Octagons are even worse. Sorry, guys. Hacking up a lung here. It's a good thing I have two. Let's see. So it's tetraene, right? And we could draw that here as well. I think that's 8 sides, right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So these frost circles are cleverly devised to also reflect the shape of that molecule. But look what we have going on here, right? These pi bonds are also going to end up in non-bonding molecular orbitals, okay, based on how that molecule is arranged. It's got more non-bonding, sorry, more bonding, but because it does have that in the non-bonding molecular orbital, it's just not as stable. It doesn't mean it's going to fall apart necessarily, but going back to this here, you see that they're all
Okay.
in bonding.
And that explains the
That
stability, the
explains why
higher.
benzene is so darn stable.
It's the paired electrons in each orbital. And
Paired electrons, all in bonding
Bonding
molecular orbitals.
Okay.
Little interference, right? So no node, great. One node, not as good, but still better than multiple nodes. And also, even though there's a node there, it's still in a bonding molecule. So that is what makes benzene stable. That's what makes aromatic rings in general stable. Okay? Not all cyclo rings with pi bonds are going to be aromatic.
Okay.
And that's what we're going to get into next. Okay. Right? This is not aromatic. It looks a whole lot like benzene. It's a little different, right? It's not aromatic. We'll get into what makes things aromatic. Okay. Right here. So Huckel's, or I think it's Huckel's rule or law. In order to determine if something is aromatic, it has to satisfy a certain criteria. Okay? The first criterion being it has to have conjugated pi bonds, and it must be cyclic. Okay? You guys remember what a conjugated pi bond is versus an isolated pi bond? Sean went over those.
The orbitals overlap.
Mm-hmm. And so they're going to be in proximity to each other. If you have an isolated pi bond, it's out there in the back 40, right, all by itself, hence isolated. So, I mean, we've got that with the cyclooctatetraene, but that's not the only criterion, okay? The other thing is that we have this 4n plus 2 pi electron rule. In other words, if you take 4 times any number plus 2, whatever that number is, and that is your number of electrons, then you're good. So for instance, let's just say n is 1. 4 times 1 is 4, plus 2 is 6. So if we have 6 pi electrons, we've satisfied that criteria. Right? If we have 4, notice 4 is not in there. Okay? 12 isn't in there, right? Because you can't do 4 times something plus 2 to get 12. Right? 4 times 2 is 8, plus 2 is 10. Oh, there's 10. 4 times 3 is 12, plus 2, 14. Okay? So that's the total number of pi electrons. You could also look at the number of electron pair, okay, if that's easier. I tend to think that's easier. In the book, and I haven't checked the OpenStax book, but in the Klein book, they always refer to it as 4n plus 2, so that's why I have it here, just so it's not confusing, but it could be 2n plus 1 if we're talking about electron pairs. Okay? This is total number of electrons. And it turns out if you have an odd number of pi bonds, then you've satisfied these first criteria, then you're going to be aromatic.
Okay.
So for instance, let's look at this. Is it cyclic? Yeah. Does it have conjugated pi bonds? Yeah. So the next thing is, how many pi bond electrons are there? 2, 4, 6, 8, 10, 12. Doesn't satisfy the 4n plus 2. Or if you just want to say, well, how many pi bonds are there? 1, 2, 3, 4, 5, 6. Not an odd number. So, right? So not all cyclic rings with conjugated pi bonds are aromatic. And that means that they're not all going to have that stability. With aromaticity comes increased stability. Remember we talked about on Tuesday how you take a hexane and you hydrogenate it, or you take a hexene, cyclohexene, you hydrogenate it into just a cyclohexane. There's a certain amount of energy that's released, right? If you have a cyclohexadiene, you hydrogenate that, it's almost double, right? But then when you take an aromatic ring that has 3 pi bonds, it's not triple. Because the aromaticity of that, and we use benzene as the example, right? We could have used other aromatic rings, but the aromaticity of that makes it stable. going back to this, where was that? Here,
Yeah.
right? This is not aromatic, right? How many pi bonds does it have?
2.
2. Even number. This is not aromatic either because,
Not
yeah, it has an
conjugated.
odd, but it's not conjugated.
Yeah. Okay.
Okay? It's not until we get to benzene that we have the odd number and the conjugation. Thus, that increased stability.
So benzene's like the smallest aromatic compound then?
That's a good question. I think so. Yeah.
Looking at the rules, it seems
Yeah,
that
I
way.
don't think
yeah.
you could get something. Well, technically you can have 2.
Oh, okay.
So if you had something that was
But it wouldn't be conjugated though, would it?
conjugated. That's a good question, Rob. I don't know. What?
Sorry, I wasn't trying to throw you a curveball.
There's got to be some example, So let's look it up as homework. Also, homework. We're gonna go over some NMR and IR stuff. I passed out a little handout on that. That might look familiar. Sean may have. I know Sean must have gone over NMR and IR with you folks, right? Yeah. And then also here, this is a list of different types of molecules that are either activators or deactivators. Does this look familiar at all? Did he talk about activators or deactivators?
Remember that?
Electron donating, electron withdrawing.
Yeah, a little bit.
Okay, that's
Okay.
just another word for those things.
Okay.
Okay.
Is it similar to acid base or
What's that?
is it similar to acid and base? Or no?
Well, you could think of it that way. Because a base is something that accepts, right? Acids are donating. Those are protons.
Oh, okay.
These are going to be electrons.
Oh, okay. I see. Cool.
What do the directors do? The orthopair directors and the meta directors?
So that means that it creates a molecule that's got to be either ortho or para. So when we're doing synthesis and we use any of these as our precursor and we want to make something, right? It's going to make it as either ortho or para. If we use these down here, our product will be meta.
Okay.
So, hopefully you've saved your materials from the last couple quarters because the way OChem works with these synthesis concepts is that you are essentially constructing a toolbox, and you're gonna have all these different tools on how to make stuff, right? And so, was your final last quarter was some kind of synthesis project, right?
Yeah, like a write-up. Yeah.
You got to look in your toolbox and say, okay, how can I get from here to here? What reagents, right, do I start with? This is just building into that more, okay? And this will be relevant to some stuff we'll talk about today. But the IR and MR stuff, we're going to talk about that in terms of aromatic compounds. So if there's time, I'll go over a little bit on that sheet so we can refresh ourselves. If we see a broad peak, what does that mean? If we see a narrow peak,
Okay.
peak splitting, what is peak splitting? Up or down, all of that. And then I'd really like for you guys to brush up on that so that we can then probably next week just put a couple examples up here and see if we can solve it. Cool. Okay? All right. Okay, so. Oh, wait a minute, we didn't finish up this. What about this one? Conjugated. It's cyclic. There are 2, 4, 6, 8, 10, 12, 14. So that's aromatic, right? Or 1, 2, 3, 4, 5, 6, 7, odd number, that's aromatic. Conjugated, cyclic, 2, 4, 6, 8, 10, 12, 14, 16.
No.
Not aromatic. Or 1, 2, 3, 4, 5, 6, 7, 8. Right? It's deceptive, right? You can't just, unless you actually count those bonds, to me, there's nothing that shouts out why one would be more stable than another, or why one is aromatic and one isn't. Okay. But it all comes down to that molecular orbital, the number of bonding orbitals, the amount of interference that's caused by just having one more or one less pi bond. All right. So let's do some practice. For this first one thing that we haven't yet introduced is the idea of lone pairs. Because you may or may not remember that lone pairs can undergo resonance. Okay? And this first one has an oxygen. How many lone pairs are on that oxygen? 2. But as it turns out, only one lone pair on an element can participate in resonance. Okay? So we don't count both those lone pairs. We would say, okay, one lone pair can resonate in that structure. So if that's the case, how many, it's cyclic, all of these are cyclic, right? All of these are conjugated, except for this. Maybe this is the example of what the 2 would be potentially.
Oh, okay.
Yeah. We'll get there and see what we come up with. But how many pi bonds? Or 2, 4, 6, 8.
Okay.
4 times 1 is 4. That's we can get 6. 4 times 2, we can get 10, but we can't get 8 electrons. Right? And remember, if you have multiple lone pairs, only one of those lone pairs can resonate.
Okay.
So this would be non-aromatic. Yes, it's cyclical. And it's saying aromatic, non-aromatic, or anti. Anti-aromatic is even less stable than non-aromatic. There's no conjugation.
Okay.
Okay? So pretty much all of these I think are going to be either aromatic or non-aromatic. And sigma bonds are never delocalized, so they cannot participate in resonance, right? Going back. Did you do resonance in Chem 1?
Yeah, the first.
Probably.
Yeah, for the fall.
Never goes away.
Yeah.
All right, B. Okay, that it has the lone pair drawn in there. So what do we have? We have 1, 2, 3, 4. Even number. So what is it?
Not.
Non-aromatic.
Yeah. What do you think about C? lone pair are possible. Nitrogen can have one lone pair.
Sulfur too.
What about sulfur though?
I think so. Like oxygen.
Yeah, two. Right? So, what does that do to our total number of essentially pi electrons?
Would it be 4 or?
4. Yeah. So 1, 2, 3, and only one of these can participate. 4. So again, non-aromatic. Okay. What about D? Oh, what's that? Yeah, actually,
4, 5.
the same reason. Actually, C. This can't resonate.
Oh, because it's right
It's
there.
got a pi bond there. So
Yeah.
sorry, that's my bad.
Oh, okay.
So this is really 1, 2, 3.
3. Okay.
Yeah,
Yeah.
overlooked that. Still brushing the cobwebs off. Same with this, right? There's a lone pair here and a lone pair here, but they can't participate in resonance because there's already a pi bond there. So 1, 2, 3, aromatic. All right, you want to work on those bottom ones? Give you a little bit of time. You can work together, talk it out, or by yourself, whatever you prefer. Fine with me. about this one?
So with the charges, it means that the pi bond or the lone pair is like participating in a bond with the hydrogen, right? Yeah.
It's protonated, so no pi bond.
So it's just the third. So I would say yes.
2, 3, yeah, aromatic. Was that aromatic or non? Non, yeah, because
Mhm.
no lone pair,
Mhm.
right? Because it's protonated.
Mhm.
So it's just 1, 2. That would be now. What if what if we got rid of one of those hydrogens?
For F.
It'd be this. It'd be like that other one, right?
Mm-hmm.
No, it wouldn't.
Oh right.
Because this has a pi bond.
Yeah.
If we deprotonated this, it's not the same, right? Because it's got that pi bond there. So this could be a lone pair.
If it was deprotonated.
If it's deprotonated,
Then it would be aromatic.
Is that kind of like how G is? The next one? Would that still have a lone pair?
Mm-hmm.
yeah. Yes.
Okay. Yeah, good catch.
Exactly. So then this could participate in resonance, and then it could be aromatic.
Mm-hmm.
But in this form, not. And yes, Nikki, same thing here, right? We have lone pair here. 1, 2, 3, aromatic. All right, now, what about this?
Does that count as a conjugate? Or
Look.
Well,
is it?
when there's resonance, yeah.
Okay.
So, because these nitrogens aren't further protonated, they have lone pair, and those lone pair can come in. Right? And technically it's conjugated. So technically, this is aromatic, even and it's going to be somewhat stable, even though it has this gnarly constrained configuration, right? This is the 90 degrees that is not great, right? Molecules don't like to be in that strained conformation, but with these lone pair, it can resonate, and it can resonate 1, 2, 3, making it aromatic, making it a little more favorable. All right, now if one of these were protonated, wouldn't work, right? If we put an H there, then we just have 2, right?
Okay.
So would not be nearly as stable if I fall apart. All right, let's take like a 12-minute break, come back at 11. I saw somebody walk by